look forward to that. We gotta kind of focus on the present, right? We got 3 weeks between now and Christmas. Again, it's short this year. Thanksgiving was late, so that's a little bit different. It's only 3 weeks. After we get back, and talking about in January, so after we return from winter break, there's basically 2 weeks and then finals week. So we're real close to the end of the term here in a lot of ways, and with the holidays stuff in between of them looking ahead, it sneaks up on folks. So again, not trying to scare you, I'm just trying to give you that reality check. That if you're looking towards Christmas break and you miss the next 3 weeks, that can be kind of a bummer. And then of course Christmas break, you should go home and eat a bunch of food and open a bunch of presents and not do a bunch of homework. So don't back yourself into a corner, because again, when we get back, it's 2 weeks and then finals week. And I think there's even like a Monday off in there somewhere. There's like a variety of weird things after we get back in January. It's just going to go by fast. That was all I wanted to remind you of. Like, welcome back. It's good to have you guys here. But I will turn the clock over. Mr. Riley. Hey.
All right. Welcome back, everybody. Couple things. On the lectures where I'm going to be here, I'm going to try and record the board work and my speaking and post it on YouTube with the link posted in Canvas. So if you missed something in class, if you need to go back and double check how we did one of the problems or something like that, you should be able to find that in the recording. Or if you need to be absent for any reason, you can always go back and check the recording. I'm not great at video editing or anything like that, so I'm not going to do that. So they're not meant to replace you being in class, because they're not super fun to watch. It's going to be a recording of the whiteboard for an hour and a half, with me talking over it. So definitely better to still be here, but if you do want that extra help, need to double check something, you can go find that on the Canvas shell. I'll just keep posting the links to YouTube links as we go. Don't start with some review. We ended talking about pressures and volumes, and I set the table for how you're going to do this week's lab, which is basically enclose a system of gas, change what the pressure is, and then look at what the volume does. And we thought in general, if we looked at pressure on the x-axis and volume on the y-axis, we start from some point here. If we increase the pressure, what should happen to the volume? We would expect if the pressure goes up, that means the volume is going down, and it does have that inversely proportional relationship. Where if this is 1 atmosphere and this is 2 atmospheres, we double the pressure. This is 1 liter. We expect this to be 0.5 liters. Right? We talked about what happens if we extrapolate that out. If we did a logic experiment, if we kept doubling this, will we ever get to 0 volume? Not unless we get to infinite pressure, right? And we know that infinite things don't really exist in the universe, other than maybe the universe itself, and even that's up for debate, depending on who you talk to. So really, we can't get to an infinite pressure. In the real world, what happens if you do this? If you keep increasing pressure on a gas, either your container is going to explode, or you go through a phase change. We're assuming no phase changes are going to happen here. Right? All of these simple gas laws, we're assuming that the gases behave as an ideal gas, which basically in physics and chemistry, when you hear something as an ideal model, that usually means we're making some assumptions. Right? In this case, the assumptions we were making are no phase changes. And we'll talk about phase changes in more detail next week, maybe on Thursday. Then anybody remember what the other one was? If you could put if we actually did get this down to close to infinite pressure, volume of what? The gas molecules themselves take up space. Right, so we're assuming that the volume equals 0 for the gas molecules. And those are decent assumptions for the most part. Right, under normal conditions, which I'm going to say is Earth-like conditions, these are pretty valid assumptions. When you start getting into things like gas giants or really, really high density systems, these assumptions aren't good anymore. Because if you have a whole bunch of gas molecules in a tight space, this assumption doesn't hold up anymore, right? Because now all of a sudden the gas molecules will start taking up a measurable fraction of the total volume. And if you do compress it enough, you'll get phase changes happening. You'll force the gas to turn into a liquid or to a solid. Turns out just everything has a melting point in almost everything, or sorry, everything has a boiling point. Almost everything has a melting point. I don't think that we've observed any cases where hydrogen was a solid, but we've seen some properties consistent with the behavior of a solid if you get hydrogen cold enough and compressed enough. But hydrogen boils, liquid hydrogen boils at like negative 270 Celsius, which is about where helium boils. You can actually get liquid helium too, but it's really cold. And we'll talk about temperature in more detail here in a second. All right, we also said what happens if we do the opposite. If we cut the pressure in half, what's going to happen? We would expect the volume to double. And basically, how do you, if you added a bunch of pressure to a system, a closed system of gas, like you took a balloon and you squeezed it evenly from all sides, and then you got it so that it was at this nice 1 atmosphere pressure, what happens if you let go of the balloon? It's going to expand, right? If you had to add extra pressure around the balloon to get it to compress, when you let go, it's going to go back to where it was, right? So we have a nice 1 over x graph here, which led to this equation. So our first review problem here, we recap some of the logic there. Similar problem that we had the other day, except I changed the numbers. A 750 ml bottle is sealed at 612 torr, which is about our normal barometric pressure up here at lake level. What is the pressure in PSI if you then squeeze it until it's 0.65 liters? So you took a system of gas and you compressed it. Qualitatively, what should happen to the pressure? Pressure should go up, right? Like picture taking an empty plastic water bottle, putting the lid on it, and then squeezing it. The pressure inside the bottle goes up when you do that, right? How much does it go up? Let's just do the math. What's P1? Okay. Do we have a value for it? Yeah, it doesn't really matter which pressure we picked, the P1 versus P2. By convention, we do whatever the initial system is, we call that 1. And then whatever exists after the change, we call that 2. Mathematically, it doesn't really matter which way you go. So we can say P1 is 612 torr. What's V1? 750 milliliters. Did I fix the ambiguous number there? Did I forget? I did add the decimal point there. What's P2? We don't know yet. Are we good to just plug everything in and solve? Always double check your units, right? Liters here and milliliters there. We just want it to be consistent. Doesn't matter which one you convert, just pick one. Either convert liters to milliliters or the other way around. So 612 torr. 0.750 liters equals P2 times 0.65 liters. So we cut by like 0.15, so it should be about 15% higher than that. So somewhere in the 640 range. No, I did that math wrong. 15% is going to be 90, so somewhere around the 700 torr range. How many sig? 706. What are we done there?
No.
Why not? Just have to put it in PSI. And then remember, we only had 2 sig figs on our final volume, so we're going to round it to 2 sig figs. We can do that after we convert to PSI, though. So 706 torr. What's the conversion torr to PSI? 760 torr is atmospheric pressure, standard atmospheric pressure, and 14.7 PSI is standard atmospheric pressure. So we get somewhere in like what, 12.5 range? I could be off on that. $13.7, which we're then going to round one step further, right? So 13.7 PSI, we got to round it to 2 sig figs, 14 PSI. Okay. I have this habit where I pick up an eraser and then I'll walk around and set it down someplace. I did not do that, did I? Yeah. Which? All right. How do we feel about these? It's easy as long as you know the units, right? As long as you pay attention to the units. You do have to read the problem a little bit to figure out and look at the units to figure out what's P1 versus V1, right? We know if you just know 750 milliliters and that's not called out as the initial volume, you have to know that milliliters is a volume unit, right? Other than that, these aren't too tricky. So let's make it more tricky. What did we have to have happen for this gas law to work? For P1, V1 equals P2, V2, what had to be true? We made those two assumptions. What else had to be true? Look at the problem statement.
Constant temp.
Constant temperature. If you don't change the pressure, if you don't change the volume, take your sealed plastic water bottle. If you change the temperature of that sealed plastic water bottle, but you don't change the volume, what happens to the pressure? You got three options, right? Increase, decrease, or it doesn't change. Has this ever happened to you in real life? You ever closed an empty water bottle, left it in the car? What happens when you open it? Gas comes out, right? So what's happening there? What are the two things that affect pressure in our initial definition of it? It was force over area, right? If the volume's not changing, then area is not changing. But if you change the temperature, if you increase the temperature, that's going to affect pressure too, right? Because all those tiny little molecules are going to be moving a little bit faster. If they're moving faster, what happens when they hit the wall? They're going to hit the wall harder and more frequently, right? So we would expect that increasing the temperature is going to also increase the pressure. What else had to be true for this to work? We had assumed we're at constant temperature. What else had to happen? What if we tried to do this experiment without sealing it? If you just took an empty water bottle, said, this is a system of gas molecules, without putting the lid on it, and then you squeezed it. All the extra gas molecules come out. You didn't really change anything, right? So we're also assuming that it's a constant number of gas molecules. If you change the number of gas molecules, is that going to change your pressure? Why? What changes out of these? Yeah, if the total amount of force has to be changing, right? Because if you have fewer gas molecules bouncing around, they're hitting the sides less frequently, right? So let's picture that in our analogy of having a box full of ping pong balls. Have I used that analogy with you yet? Think of the gas molecules as just ping pong balls floating around in a moving box. You shake the box, they're moving around, bouncing off the walls. What's the total force of the ping pong balls on the walls? That's your pressure. You take out some of the molecules, some of the ping pong balls, you're not going to have as much force on the walls, right? So there's a few other variables that are going to affect this. The first one that they started looking at was temperature. Now, they didn't actually look at changing the temperature with a constant volume, because what happens if you get a closed system of gas and you start heating it up? What happens if you have a constant volume? Pressure goes up. What happens if you go too far, though? Explosion. Right? So they actually did this experiment the first time. This is Charles' law. Charles' law. First one was Boyle's law. This one is Charles' law. Any Brooklyn Nine-Nine fans? I don't think that they named the character Charles Boyle after Boyle's law and Charles' law, but maybe they did. Something to think about. So Charles actually did this experiment with a piston where he sealed the container, and then he had a constant pressure, because if you expanded this piston is pushing against the outside pressure, right? So we could say that the pressure inside the piston is the same as the pressure outside of the piston. So we were able to say for a constant pressure with a constant number of gas molecules, we expect that doubling the temperature doubles the volume is proportional to. All right, so is volume is proportional to temperature. That's our hypothesis. So similar to what we had with pressure and volume, where if we doubled the pressure, the volume cut in half, right? That's inversely proportional. In this case, we expect that if the temperature goes up, the volume should go up, right? And if you double, we would expect that, okay, well, if we sit here at 20 Celsius and we're at 1 liter, if we double the temperature, what would we expect the volume to do? If it's nice, clean mathematical relationship, that's what we should see, right? So we did this experiment. The problem is that's not what we saw. Again, slides aren't working for this part, so I'll do it on the board. If this was true, what would happen at 0 Celsius then? We would have 0 volume. Do gases mysteriously go to 0 volume when you hit 0 Celsius? In fact, can you have negative Celsius? If this was true, when we got to negative Celsius, what should happen? Can a gas occupy a negative volume, an inverse volume? That wouldn't make any sense, right? So right off the bat, that tells us, if we just thought about this a little bit harder, we can see, oh, well, obviously this can't be right, because we can have negative temperatures in Celsius or Fahrenheit, which means doubling a temperature in Celsius is not going to actually double the force. Right? We can't double the force this way. We need something so that when you got all the way out to as cold as you can get. So when we actually did this, they did this experiment, they looked at a bunch of different pressures, and they found that the line looked something like this. That's not what we want. That does not mean volume is proportional to temperature. Proportional means it has to go through the origin. But this does mean that, okay, so if this is at 0 Celsius then, how could we figure out where the volume is going to be 0? You all actually already have the math for this if you've taken first year algebra, freshman algebra. How can we tell where the volume is going to be 0? What do we call that in math? Technically, it's the x-intercept. That's the y-intercept. We want the x-intercept. Basically, if we have the equation for this line over here, we can just go all the way over here and say, okay, well, this temperature here, where the volume gets to 0, that's got to be the coldest possible temperature that you can get. Because there's some temperature where the volume of your gas drops to 0. Not really, because we're assuming this is an ideal gas. Really, what happens if you get a gas really, really cold? It condenses or it turns into a solid, right? But if we're assuming no phase changes, there should be a temperature that is as cold as you can get. What do we call that temperature? Snowy? Absolute 0. The term absolute 0 is referring to this idea that there is some point where you can't get colder. Which actually kind of makes sense. It's weird to think about because we're used to thinking about temperature scales where you can have negatives where you can go below zero. But it actually kind of makes sense. If temperature is how fast the molecules are moving, well, that means that there's a theoretical minimum temperature, right? Because what happens when you get to absolute zero? All the movement stops. You can't get colder than that because you can't go slower than stopped. Right, so this temperature, this is actually the first experiment where they were able to come up with a value for absolute zero. We know what absolute zero, the temperature is, by just looking at this graph. We don't actually have to reach absolute value or absolute zero. We actually can't reach absolute zero. Because what happens if we cool down our box of ping pong balls, our moving box full of ping pong balls, to the point where all the motion of the ping pong balls stopped? What happens to the ping pong balls when I set it down? They move. Just a tiny bit, but they move, right? So even if I could get it perfectly cold to absolute zero, as soon as you do that, in the real universe, something bumps into it. And now it's not at absolute zero anymore. Right? Anybody know what this number is?
32.
32. No.
Thanks.
Negative 273.15 degrees Celsius. Pretty cold. For reference, liquid nitrogen boils at about negative 200 Celsius. So this is another 70 degrees Celsius colder than that. And I mentioned liquid helium boils at it's about 270, negative 270 Celsius. So really, really cold. If we do the experiment with a different temperature scale, basically when they figured this out, they looked at this, the equation for this line, we expected volume to be proportional to temperature, and it wasn't, because we could have negative Celsius. All they did was to make a new scale, they basically said, okay, well, what if we took that negative 273.15 Celsius, we're just going to call that zero. They just shifted the origin over in math terms. Say, okay, well, we're going to have a new temperature scale now, where the slope is still the same as Celsius. We're just going to call it Kelvin. It's not degrees Kelvin. You don't use the degrees symbol for Kelvin, because degrees technically means that you picked a start point and an end point, and then you evenly distributed it between that. This is not degrees Kelvin, it's just 0 Kelvin. So to get from Kelvin to Celsius is a really easy conversion. Because we said, okay, let's make the slope of the line the same, we're just going to shift the origin over. You just take your temperature in Celsius and you add 273 to it, and that gives you your temperature in Kelvin. If you're in Kelvin and you want Celsius, you're going to subtract 273.15. So really easy conversion. It's not a conversion like a conversion factor, right? All it is going to be adding or subtracting a constant. So if we double the absolute temperature, meaning if we double the temperature in Kelvin, now it turns out this relationship does hold true. So if we're in Kelvin, you can say doubling the temperature doubles the volume. Basically, we're going to do everything in Kelvin as much as we can, because it's going to make a lot of these math equations work a lot cleaner. You can write an expression between volume and temperature, but it's going to be y equals mx plus b. It's going to have that constant intercept in there. We don't want that. that makes life more complicated. We'd rather have a straightforward conversion or gas law that looks like this one. So the way we do that is we just do everything in Kelvin from here on out. And that also means we had a nice clean gas law go with this. If volume is proportional to temperature, that means that volume is equal to a constant times temperature in Kelvin, which means we can do the same thing we did to get this gas law. If we just solve for this constant, we just multiply both sides or divide both sides by T, we can get volume over temperature equals a constant, which means for a closed system of gas at a constant pressure, we can say that V1 divided by T1 equals V2 divided by T2. And so basically the way these gas laws are going to work is we're going to have, are there four? I guess there's three simple gas laws that then we wind up combining. Basically the only tricky part about these gas laws is being able to look at the units and know, am I dealing with temperatures or am I dealing with pressures or am I dealing with volume? As long as you can look at the units and tell whether you're talking about volume, temperature, or pressure, then these simple gas laws are just that. They're simple. So let's try this problem. You have a sealed 1 liter system and it's heated from 22 Celsius to 51 Celsius at a constant pressure. What's the new volume? So if we've got pressure is constant, volume changing, temperature changing, what's V1? 1.0 liters. What's T1? 22 even? 22 plus or minus a degree. We have T2, 51 degrees Celsius. And we're solving for V2. We ready to just plug everything in?
No.
What do we need to do first? Just have to put it in Kelvin. So 22 plus 273 is 295. 51 plus 273. It's going to be what, 324? As soon as we're in Kelvin, now we're ready to plug it in. I know somebody out there is wondering, well, what if I wanted to use Fahrenheit instead of Celsius? Well, you can do that. You just can't do it for this gas law. Unless you use, there is an absolute temperature scale in Fahrenheit. If you do the same thing to Fahrenheit that we did with Celsius, where you just shift the intercept over, you actually can get a temperature unit called Rankine. Which is basically an absolute temperature scale in Fahrenheit instead of in Celsius. I've never actually heard of anybody using that, but it does exist. So if you choose to be really, really picky and avoid the metric system at all costs, the only people I can think of that might use this is if there was a particular engineering firm that insisted on everything being in imperial units instead of in metric units. So an American engineer might use Rankine. But all of the engineers that I know really just use the metric system when it matters. So I don't even really know why that exists, but it does. So we need to be careful. We want our temperature scale to be in Kelvin. If you just stick to Kelvin, then you can ignore everything I said for the last 3 minutes about Rankine. Put it out of your mind. The imperial system isn't real. It can't hurt you. So what do we get for a volume? So V2 is going to be equal to V1 T2 over T1. We do the algebra, or if you plug the numbers in beforehand, either way, what do we get for an answer? Maybe 1.1. It's not going to change much. 1.09, so 1.1 after rounding. Our absolute temperature went up by 30 degrees, by 30 Kelvin, right? Which is roughly 10%. So I was able to look at 1.0 liters and say it's probably going to also increase by about 10%. A tenth of one is 0.1. So again, nothing tricky other than recognizing the units, then a little bit of light algebra. All right, so this is all well and good if we're doing this as a piston where the volume can change. What if we wanted to do that ill-advised experiment where we had a constant volume, but we changed the temperature anyway? What happens if we wanted to look at pressure changing as a function of temperature? If we kept the same volume, we would expect we have to be in Kelvin for this to work, just like with volume. But if we doubled the temperature in Kelvin, so at 0 Kelvin, is there going to be any pressure? Shouldn't be, right? We can't actually get to 0 Kelvin, but if we could, we'd see that there would be zero pressure there as well, because your gas molecules can't bounce against the sides of the container if they're not moving. And then we would say, okay, well then, as we increase the temperature, pressure should go up linearly. In other words, we should be able to write the same expression here, just with pressure instead of volume. And so that's actually what they did for this next gas law. They didn't actually need to run the experiment. They actually used classical geometry, meaning Euclid's axioms from ancient Greece, predating ancient Greece, because I think Euclid was working from an earlier document. Where basically you can say, okay, well, if we know both of these things are true, if pressure times volume is equal to a constant, and volume over temperature is equal to a constant, we can basically say, okay, well, if that's the case, we can basically substitute in pressure for volume here. So the next simple gas law is Lusak's law, and it's P1 over T1 equals P2 over T2. So basically, taking Charles' law, you replace the volumes with pressures. How are we going to remember all of these? Great questions. The answer is you don't. I mean, you can, but you don't need to. Because we can do the same sort of thing here that we've been doing. A system is sealed at a constant volume. Temperature has changed. What's the new pressure? They start getting really repetitive, right? It turns out if we have the only other variable in here, there's one more simple gas law that we need to get where we're going here. What did all of these gas laws have in common? So for this one, it was constant, a sealed container at constant temperature. This was a constant pressure. This was at a constant volume. What's constant with all of these? Each other. What happens if you do this experiment if you take a system of gas and you heat it up but you don't seal it? What changes? Same thing as if we change the volume without putting the lid on our water bottle, right? All of these were assuming constant number of gas molecules. So the last variable, this is Avogadro's law. So same Avogadro of Avogadro's number. I think that he actually came up with Avogadro's number as a way of measuring gas laws. I want to say that the research was happening in the gas laws first. And then he said, well, we need some way to count these objects, so I'm just going to invent them all. But Avogadro's law is basically saying, so what happens if we change the number of gas molecules? So we use the variable lowercase n for moles, and that comes from just number. If we're counting all of the objects, we'd use capital N. That's just the number. Lowercase n is number of moles. So if we have our box full of ping pong balls, we're counting every impact with the sidewalls, adding up all that force. If we double the number of ping pong balls, what happens to the force? We would expect the force to double, right? Twice as many objects means twice as many collisions. Twice as many collisions means your force doubled. So we would expect if we double the number of gas molecules, our pressure increases as well. And that is, in fact, what they see. And we don't need an absolute temperature here because counting objects is already an absolute scale, right? We're not talking about having negative molecules. We're talking about real objects. What would even a negative ping pong ball look like in our analogy? You can't have a negative ping pong ball. You can't have fewer than 0 molecules. So we got another expression that looks like this. P1 over N1 equals P2 over N2. All of these look really similar to each other, right? They're all describing different gases. So we actually have a way of combining all of these simple gas laws into one that we call the combined gas law. Because if these are basically all the different variables that are going to control, that are going to be needed to describe a gas, we can put them all into one equation we call the combined gas law. So the combined gas law has two forms. Basically, we can say, as long as any one variable is held constant, we can say P1 V1 over T1 equals P2 V2 over T2 for a constant number of gas molecules. So this is the first version of the combined gas law, but this isn't the real combined gas law. This isn't even its final form.
So do we need to separate?
No, and they're not on your conversion sheet. Because the super leveled up version, it's not that much more complicated. As long as any one variable is held constant, you can use this equation. Which means it doesn't have to be n that's held constant anymore. We don't need to hold the number of gas molecules constant. Number of gas molecules can change. As long as one thing is held constant, we can use this. So this is the version that's on your conversion sheet. Because this has all the others built into it. Because if moles of gas is held constant, what's true about this equation? If moles of gas is held constant, what do we know about N1 and N2? They're the same, right? If they're the same, I can just multiply both sides by N1, right? If I multiply both sides by N1, what can we do? And we get the simpler form of the combined gas law. What if temperature is held constant also? If temperature is held constant, the same thing happens. Temperature cancels out. And what happens when we rewrite that now with everything canceled out? What do we get? P1 V1 equals P2 V2. So you don't need 5 different simple gas laws. You just need this one. And then anything that's held constant just cancels out on both sides. You just cross it out. Right? So this is the form that's on your conversion sheet that you'll have with you on the final. If temperature is changing, but moles of gas and volume are not, everything cancels out. We get this law, right? Anything that's held constant, you just cross it off because it's the same before and after. Let's see. I think I have a practice problem. All right. You have a 2-liter bottle. And you leave it in the car on a hot day and it reaches a temperature of 48 Celsius. If your initial pressure was 610 millimeters mercury and initial temperature is 27 Celsius, what's the final? That's wrong. What's the final pressure in millimeters of mercury? All right, it's a sealed container. So what's being held constant? N. Moles is held constant. Sealed means we're not losing or gaining any gas molecules. Right? That's what sealed means. It's one of those word problem clue words. As soon as you see sealed, that means your number of gas molecules is not going to change unless you've got a chemical reaction happening. So we don't need this. Everything else is changing though, right? We've got changing temperature, we've got changing volume, and a changing pressure. All you need to do is recognize the units though. Right? There's really, the more things that are changing, the more I have to give you because you can't solve it unless you only have one unknown, right? So basically, it might make the problem look more complicated, but I have to give you more pieces if more than one variable, more than 2 variables are changing. So what's T1? Don't just read left to right. Initial temperature is 27. So 27 degrees Celsius, which is going to be what in Kelvin? What's T2? The other one. Temperature afterwards is 48 Celsius. Which is going to give us 321. What else do we know? We know P1 is what? Our initial pressure, 610 millimeters mercury. And volume 1 equals 2.0 liters. Say anything about volume changing? So we're given an initial volume. We did this with a 2-liter soda bottle. It's empty, close it. Does the soda bottle change shape much when it gets hot? Some water bottles made out of really thin plastic, they'll expand a little bit, right? If we did this with a balloon, the balloon could change volume. It's telling you it's a 2-liter bottle, but then it doesn't say anything about the volume changing. If you're not told that the volume is changing, what can we assume? Volume's constant, in which case the volume, that 2.0 liters, doesn't actually wind up mattering, right? It's a little bit of a red herring. Volume's not changing, so that cancels out too. So we don't even need that. So really, we've got P1 over T1 equals P2 over T2. (610 millimeters mercury over 300 Kelvin equals P2 for 321 Kelvin. So we get something, pressure doesn't change that much, right? What, about 670? 670. (610) over 300 times 321, 652. See, 653 after rounding, right? What's the other name for millimeters of mercury? Torr. So I don't like writing millimeters of mercury very often because it feels confusing to me, because millimeters is a distance, not a pressure. So I usually will write it as torr. And because it is one of those 1-to-1 conversions, sometimes I won't even show the conversion, and I'd be okay with that. If I said what is the final pressure in millimeters of mercury and you wrote torr, I would be okay with that. As long as you know that it's 1-to-1. Just like there's another really common conversion that's 1-to-1 that we hardly ever show our work for. Has to do with volume. No? How many milliliters are in a liter? 1,000, right? On your conversion sheets, there's a conversion for cubic centimeters to liters. Anybody know how many cubic centimeters are in a liter? Also 1,000. So basically a cubic centimeter is a milliliter. That's another straight 1-to-1 conversion. I'm not going to mark you down if you don't show the conversion from milliliters to centimeters cubed, because half the time I forget to show that work, right? It's a straight 1-to-1. I will be careful when I ask you questions not to assume that you know that. And if you ever see me writing, if you see me go from cubic centimeters to milliliters on the board and I didn't show the work, feel free to ask me to show that conversion. It's just a 1-to-1 conversion. But I do forget to do that sometimes. And I won't mark you down for forgetting. All right, is this everything we need to know about gases? Almost. We're close. There's one more thing about this combined gas law that actually has a slightly different format. Remember I told you there's 2 versions of this? The other one has a different name. When we were doing these derivations, we went back to the volume is proportional. We said volume is proportional to temperature. Then we could say volume is equal to a constant times temperature. Does that look familiar? And then we said, okay, divide both sides by temperature, and we got V over T equals a constant. That's how we did all of these simple gas laws. We started by saying, okay, well, they're proportional. Therefore, we can say they're equal to a constant. And if they're equal to a constant, we can say V1 over T1 equals V2 over T2. If we use that same sort of logic with that combined gas law, that means that P1 V1 over N1 T1 is equal to a constant, which is equal to the other side, right? In order to use the combined gas law for this, sorry, these words should be 2s to be consistent. We said, okay, assuming any one variable is constant, we're just going to cancel it out from both sides, right? What if all 4 variables were changing? Well, the equation still works, right? But if we're not talking about a sealed container of gas anymore, if we're not holding any of these things constant, is it really the same gas to begin with? It could be all new molecules, right? If we're changing the number of molecules, changing temperature, changing volume, changing pressure, it's not really the same gas sample at all anymore. Basically, we can say that all gas molecules, all gas systems are equal to a constant. And it turns out it's the same constant for every system of gas molecules. So since it's such a fundamental constant, it gets its own letter. Capital R. Capital R is called the ideal gas constant. And it turns out it's actually not really related just to gases. It's actually a fundamental rule for how statistics and probability works in our universe. Is anybody seen that movie, The Theory of Everything? It's the theory of everything doesn't actually have anything to do with most of the movie, but the whole idea that a lot of these physicists in the 20th century were looking for a theory that combined all of these fundamental constants that showed up everywhere. They couldn't figure out why R was the number that it was, and how does it relate to some of the other fundamental constants. Can anybody think of any other fundamental constants of the universe? There's a gravitational fundamental constant. I actually don't know that one off the top of my head because I'm not a physicist. That's not constant. That's acceleration due to gravity, and that's specific to Earth. But there is a gravitation constant. I think it's what force of gravity is equal to mass 1 times mass 2 times capital G over the distance squared.
Yeah.
That G, or that 9.81 figure that shows up, is basically combining the mass of the Earth with gravity, with this G term, and assuming that R is small enough that it's not really going to matter. So basically 9.81 is constant. Actually, it's assuming that R is the distance between the center of the Earth and the surface of the Earth is a constant. If you actually get off of the surface of the Earth, or if you're not on Earth, you have different masses and you have different distances, so you can't use the same equation. But G is the same. Again, this is a chemistry class, not a physics class, so I'm not going to make you do any of that because physics is physics. The other one that people usually come up with is the speed of light. Speed of light in a vacuum is a constant. So Einstein and Hawking and some of these physicists and Feynman, some of these physicists in the 20th century, their life's work that they never finished was trying to find one way to unify all four fundamental forces. After Einstein died, they were able to turn it down into two fundamental forces, basically, by showing that strong nuclear force, weak nuclear force, and electromagnetic force were really all the same thing. But gravity, we still don't have a way to unify gravity with the other roots. So, and R, I bring all that up because R shows up everywhere. R is like the speed of light. It shows up in all sorts of different units in different ways you wouldn't have expected. So R is on your conversion sheet in two different forms. Yeah. Time is not a constant. That's what relativity is all about, right? Time, and there's actually been a fair bit of research recently suggesting that, and recently I mean like in the last 30 years or so, suggesting that time is really just the way that our brains process change in entropy. That it's not constant because different species and different conditions are going to experience time differently. But that's neither here nor there. You could call the second law of thermodynamics a constant, but it's not really, it doesn't have a value associated with it. I guess Boltzmann's constant, maybe. Anyway, take Gen Chem, take modern physics, and you get to talk about all that stuff. What we're going to use it for here, the reason you care about this is because this means that as long as we don't have to talk about before and after, we don't have to have P1 V1 over N1 T1 equals R. We can just for any gas where our ideal gas law assumptions hold up, the pressure of a gas times its volume divided by the moles divided by temperature is equal to the same value. And in gas law units, R is equal to 0.08206 liters times atmospheres per mole Kelvin. So wonky looking units, right? Basically, R doesn't mean anything in gas law units. It turns out that R is actually a measure of entropy. R is in an entropy unit. If you take liters times atmospheres, you actually get energy units out of it. So the other value of R that shows up in physics and in quantum mechanics is 8.314. That's joules per mole Kelvin. And that's actually an entropy unit. Does anybody know what entropy is? This is another digression. It's not something I'm going to test you on in this class. It's not the study of anything. Entropy is a measure of disorder. Entropy is a way of measuring how many different combinations can you have. So entropy is capital S is the value for entropy. And it's the entropy of a system is equal to the natural log times, it's equal to a constant times natural log of W, where W is the number of possible combinations there are. This is another one of those fundamental constants that shows up everywhere. It turns out actually Boltzmann's constant is really just R, except per atom instead of per mole. If you take R and you divide by Avogadro's number, you get Boltzmann's constant. So the guy who first came up with this concept, this way of describing statistics this way. Again, this is not going to be on any test until Gen Chem. Basically, his name was Boltzmann, Ludwig Boltzmann. And this is literally the only thing written on his tomb. His tomb is a bust of him, and not a particularly happy-looking bust. And it just has this equation written on it, because his life's work was basically showing that all things naturally progress towards disorder and everything is falling apart. Very, very early 20th century literature. Where's the lit? You guys talked about anything past Shakespeare? Do you guys talk about T.S. Eliot and Wasteland or Chinua Achebe? Handmaid's Tale. So the modernists of the early 20th century were also all about this concept of life is falling apart and everything is terrible. The response to transcendentalism from the 1800s. You guys had to read Thoreau, right? Nobody's had to read Thoreau yet on Walden Pond? Oh, kids these days.
Yep.
It's not entirely relevant, but it's if you are into science history, it's interesting to see what happens in the literature trends, similar to when a lot of these discoveries were happening in science. At least it's interesting to me. Which means you get to hear about it. All right. So how does this actually work? Basically, if you have, this is also called the ideal gas law. If you have the ideal gas law, it means you don't really need to use those simple gas laws as long as you have enough information. And the number one way that this is going to show up on the final for this class is this is going to be another way that you can get to moles for stoichiometry. So now we have molecular weight and mass to get us to moles. We have solutions and concentrations as a way to get to moles. If you have a gas, we have the ideal gas law to get to moles. So as long as you know a pressure, a volume, and a temperature, you know how many moles of gas it is. So let's do an example off the top of my head. Let's use this room. How many moles of gas are in this room? Assuming the furniture is not taking up any space and humans are not taking up any space. When this room is empty, how many moles of gas are in this room? Well, what's the pressure in this room? Roughly. It's not 1 atmosphere. If we were at sea level, we would assume 1 atmosphere. That'd be nice, convenient. We're at about 0.8 atmospheres here. So I'm just gonna say it's 0.80 ATM. What's the temperature in this room? Really roughly, in Celsius. So here's an easy in your head conversion for Celsius and Fahrenheit. 68 Fahrenheit is exactly 21 Celsius. So room temperature is usually a couple degrees above that. So let's call it 22 Celsius in here. It's a cold day. Let's say that's about that our temperature is roughly, call it 22 degrees Celsius. Which means what for, what do we then have to do? Kelvin. So add 273 to this. If we're trying to find N, we want to know how many moles of gas are in this room. What else do we need? Volume. How are we going to estimate the volume of this room?
Yeah.
Length times width times height. So what's our height?
4 meters. 3.
Usually we'd assume close to 10-foot ceilings, or probably a little bit more than that, but let's make the math easy on ourselves. We'll call it 10 feet, which is really close to 3 meters. And then how wide is this room? 6, 7. So I mean, call it 30 feet by 30 feet. Again, let's make the math easy on ourselves. 30 feet by 30 feet is going to be really close to 10 meters by 10 meters. As long as we're making up, and we might be off by a meter, but we're not off by more than a meter probably. As long as we're making up numbers off the top of our head, we might as well pick them conveniently, right? Because that means our volume is pretty easy, right? 300 cubic meters, which if you look at the units on R, the units on R tell us what we need to do with our conversions. We want, anytime you're using ideal gas constant, you want liters, you want atmospheres, you want moles, and you want Kelvin. So we're just going to have to find a way to put cubic meters into liters, which I believe there's a conversion for that on your conversion sheet. But if you don't have your conversion sheet, that's, put it in scientific notation for the sake of sig figs, 3.0 times 10 to the 2 cubic meters. We just figured out that we have a conversion for cubic centimeters to liters, right? 1 meter, it's 100 centimeters cubed. Then 10 to the 3. Sorry, 10 to the 3 cubic centimeters. It's 1 liter. Think we wind up with 30,000 liters? Maybe 300,000? Might have slipped a decimal.
Over.
Really speaks to.
That's gonna be 10 to the 6, 10 to the 8, divided by 10 to the 3 is gonna be 10 to the 5. So yeah, 300,000. All right, we'll finish this one up on Wednesday when I'm here. Tomorrow you're doing your lab, and Wednesday you're doing the data analysis for your lab. You might want a computer or a Chromebook to take. You can talk to the administration here. I don't like that either personally. I'm totally on board with